Well, welcome again to Algebra and Number Theory, and we've been looking at Gaussian integers, and we've now proven a number of results and its connection with what numbers are the sums of squares. The next thing to say really is to try and pin down precisely when is a Gaussian integer a Gaussian prime. Is there some easy way of testing for primality in the Gaussian integers? And the answer here is yes, which is rather nice. So this theorem 9 says a Gaussian integer alpha is a Gaussian prime if and only if either its norm is prime or it's plus or minus an ordinary prime congruent to 3 mod 4 or I times an ordinary prime congruent to 3 mod 4. So that completely characterizes the Gaussian prime. So the proofs are fairly straightforward. So firstly, if we take alpha to be plus or minus ix ix, where x is an integer, then alpha's prime if and only if x is, and by theorem 6 this is true if and only if x is a prime and it's 3 mod 4. So we sort of knew about that one. It's the first case, it's the more difficult one and the more interesting one. So suppose we've got alpha is a plus ib, where neither of these numbers are 0, and we're going to suppose the norm of alpha is prime, and then I want to show that alpha is a Gaussian prime. So suppose it factorizes in the usual way, then we can apply norms to both sides. Now in this case, the norm of alpha, this is a prime, an ordinary prime number, and it's the product of two things, so either that's got to be 1 or that's got to be 1. So in the first case, if that is equal to 1, then the only way that can be true is if it's plus or minus 1 plus or minus I, or in this case we get gamma is plus or minus 1 plus or minus I. So in either case, beta or gamma is a unit, so alpha is a Gaussian prime. Conversely, if we take alpha to be a plus ib, where these numbers are not 0, and alpha is a Gaussian prime, then I need to show that its norm is an ordinary prime. So the norm of alpha then is alpha alpha bar, and I'm going to suppose that I can factorize this in some way, where c and d are integers, and the name of the game is going to be to prove that one of these numbers is 1. So at this stage then, remember alpha is a Gaussian prime, so alpha divides this and alpha divides the product of these two numbers, which are just ordinary integers, but they're also Gaussian integers. So that means alpha must be a factor of c, or alpha is a factor of d. So without loss of generality, I may as well assume that alpha divides c. Then I can write c as alpha gamma for some gamma in the Gaussian integers. I can then replace in this equation here, I can replace the c with alpha gamma, and I can cancel, so I get alpha bar then is gamma delta. But alpha bar is just a minus ib, and that's gamma delta. Now this d is an integer, so if this is equal to gamma d, then this integer has to divide the integer part and the imaginary part of this number here. So d divides a and d divides b. That in that case then that means d divides alpha, but this alpha is my Gaussian prime, and d is a ordinary integer, so the only option then is d has to be plus or minus 1. And that then shows that in that case the norm of alpha is in fact a prime, and then the similar argument works for the other case, and therefore norm of alpha is prime. Now as an example of how to use it, 2 plus I is a Gaussian prime because its norm is 5, and 5 is an ordinary prime. 7 is a Gaussian prime because it's 3 mod 4, and indeed 7i and minus 7 would be Gaussian primes. We can use this theorem now to factorize Gaussian integers into a product of Gaussian primes. a couple of examples. We're going to factorise 15, and then we'll factorise this number minus 77 plus 294i as a product of Gaussian primes. So firstly, dealing with 15, well, we take 3, we write it as 15 as 3 times 5. Now 3 is the 3 mod 4 prime, so that doesn't factorise any further. And 5 is the norm of 2 plus I. And so yes, a 2 plus I, so I can simply write 5 then as 2 plus I times 2 minus I will give me the 5. And so there I factorise this into, and these are all primes, all Gaussian primes, because the norm of 2 plus I is 5, which is an ordinary prime. Slightly more intricate number, we've got minus 77 plus 294i, which I take its norm, and the norm turns out to be 92365. We can factorise this in the ordinary integers, so it's got a square factor of 7, and 7's 3 mod 4, so we can't do any more with that. And we've got 5, 13 and 29 left. Now we can write 5 as the norm of 2 plus I, 13 is the norm of 2 plus 3i, 29 is the norm of, say, 5 plus 2i. So up to multiplication by units, this thing here is equal to 7 times 2 plus I, 2 plus or minus I, 2 plus or minus 3i, 5 plus or minus 2i. And then trial and error, you've got to decide which signs you're going to take here. So trial and error, in fact, then gives minus 77 plus this. We keep the 7, and in fact it's going, yeah, it's 7 because the norm of 7 is 7 squared. So we get a 7. We need to take the 2 plus I, the 2 plus 3i, and the 5 plus 2i. If you did it with the other k, if you put a minus there, it doesn't work. So this, again, this is just trial and error. There's no easy shortcut here to see which conjugates are the correct ones. Also note that we may be out by a unit, but that's okay. We can always multiply one of the brackets by the appropriate unit factor to fix this up. So this one you just have to do by trial and error, but it will at least tell you the which of the conjugates, or what complex numbers to look at in order to see the factorization. Well, before that, we've dealt now with sums of 2 squares, and we will look at 3 and 4 squares, but before we do that, I thought we'd just sidetrack a little bit and have a look at Pythagorean Triads, which you probably met first at school. And you probably recall from endless exercises that certain whole numbers can form the sides of a right triangle, and these are called Pythagorean Triads or Pythagorean Triples, such as 3, 4, 5, 9, 40, 41, 5, 12, 13, and so on. And the obvious question is, well, how do we get these numbers? Can we find some nice formulae that will generate all the Pythagorean triples? And I'm going to do this using a geometric method, which is quite nice. I think it goes back to Fermat, who first started playing around with these sort of ideas. So I'm going to take a unit circle, and I'm going to, I'm going to start off with the equation x squared plus y squared plus equals z squared. I'm going to divide by z squared, which gives me this. Now immediately, of course, we're now in the rationals, no longer the integers. And so x over z and y over z are rational numbers, and I'm going to put capital X to be x over z, capital Y to be y over z. And that means if we're given integers x, y, z that satisfy the Pythagorean statement, then the equation x squared plus y squared is 1 has rational solutions. And conversely, if we can find rational solutions on this curve, then we can express x and y with the same denominator, and we can get back and reconstruct our little x, y, z that satisfies the Pythagorean formula. So hence the problem of finding triads is equivalent to finding rational points on this circle. The correspondence is not exactly 1 to 1, since we can get 3, 4, 5 and say 6, 8, 10, etc. from the same rational point, 3/5, 4/5. However, if we insist that the GCD of x, y and z to be 1, then the correspondence is indeed 1 to 1. So here's our circle, x squared plus y squared is 1. And I'm going to draw a line that passes through this point, minus 1, 0. So this is fixed, and I draw a line passing through here. Elementary algebra shows that, coordinate geometry shows that the equation of this line is y equals t into x plus 1, where t is the gradient of the line. And I want to get solutions, in fact, in the first quadrant. So I'm going to insist that this t be between 0 and at that point t will be 1. So we're going to insist that t is strictly between 0 and 1. So we have a circle and we have a line with slope t, and I'm going to restrict t between 0 and 1, so there'll be an intersection in the first quadrant. Now I'm going to see where the line meets the circle. So the equation of the line is this. And observe the following. If xy is a rational point on the circle, then this is rational, then t, which is the quotient of these, is also rational. Conversely, and this is the interesting point, if t is rational, solving the line y equals t into x plus 1 with this circle, well, you simply substitute it in, and then you rearrange and you end up with this quadratic here. All I've done there is just put y equals this into here and expanded it out and rewritten this as a quadratic in capital X. Now we know that one of the roots is minus 1 because that's how we constructed our line. It had to pass through there. So using products and sums of roots, then we can say that x then is equal to, so the product of the roots is going to be minus 1 times x, which is minus x, is this one over this one, and using the minus to flip the signs around here, we get capital X as 1 minus t squared on 1 plus t squared. Substituting that back into the equation of our line and simplifying, we get y is 2t on 1 plus t squared. Now, our t, remember, is a rational number between 0 and 1, and those rational numbers give you all the rational points on the circle. And so since if t is rational, then this xy that we get from these formulae will also be rational. So just as an example, if I put t as 73 on 91, just any rational number that comes to mind, plug it into the formulae, we get xy is that, and then we can read off then, take the top 2 and the denominator for my z, and that will be a Pythagorean triple, which I leave you to check that squared plus that squared is that squared. To get our formula, I'm now going to simply put t to be u over v. Then my capital X looks like this, u squared minus v squared on v squared plus u squared. And y is 2uv on u squared plus v squared. And that gives me back to my triad. So I get x is now, of course, we could put a k top and bottom here with these, because we're looking at any equivalent fraction. And so I get x then is k times v squared minus u squared, y is 2uvk, and z is ku squared plus v squared, where k is an integer. And in order to make x to be positive, we'll need u, and everything else positive, we'll need u bigger than 0, less than v. Now, by the way, you probably guessed when you saw these formulae here, this looks a little bit like the t formulae, and you might like to go back into the picture and think about what happens if you go back to the picture here and think about what happens if you take a point on the unit circle here and then you call this angle theta on 2, and you think about the half angle results and trying to write sine and cos in terms of tan theta on 2, and you'll see the connection between them. Anyway, that's from trigonometry rather than number theory. So as an example, if we put k as 1, u as 5, v as 7, then we get the triad 24, 70 and 74. Note that the k is important if you want all triads. For example, if k is 1, you can't obtain the triad 9, 12, 15, can't be obtained from these formulae if you're just only having k to be 1. Now, primitive triads, if ABC is a triad and we're going to insist the GCD is 1, then the triad is said to be primitive. And a little thought will reveal the conditions required on this, on the u, v and k to be primitive are, firstly, you need k to be 1. Obviously, if you look back at the formula here, you need k to be 1, so there's no common factor. You need u and v to be relatively prime, otherwise again there would be a common factor. And moreover, if the u and v have the same parity, that is, if they're both odd, then this will be even, and this is even, and this is even, and so they're not going to be primitive. So you're going to need them you're going to need the u and v to have opposite parity. That is, the u and v must be both odd. Here we are here. So k is 1, GCD is 1, and u and v have opposite parity. For example, if u is 5, v is 7, then this did not yield a primitive triad, as we saw above, because both these numbers are odd. On the other hand, if you take u as 2, v as 3, you get your favourite 5, 12, 13, which is clearly primitive. In the next recording, we'll have a look at how we can generalise some of the ideas here to solve certain other Diophantine equations, again making use of Gaussian integers.